Why do you need PE for coding? Well, I could think of lots of reasons why you might, but it's a general requirement for the associate's degree at Clark. But you know, getting physical exercise, particularly when you're a coder, certainly seems like something important to me, because if you only feed and exercise your mind, your body will suffer, and of course everything is connected. So I mean, you could make arguments in favor of that, but the simple answer is it's just a requirement that Clark has put on the AST2 degree. But you put weights on your fingers when you type, you know, and get some extra aerobic workout like that. Those of you who have done Engineering 270, you may be happy to know that for the past hour I've been fighting with MPLab and found a bug in their assembler where it's not creating the proper bit patterns based on the instructions I'm specifying. So everybody has troubles with MPLab from time to time, so you're not alone.
I have a question for you about that, actually.
Sure.
I remember at the end of 270, the last assignment, we had I had some sort of bug with the
serial port.
baud rate.
Yeah.
Serial port. There you go. Did you ever figure that out?
I never figured it out. Yeah, it's peculiar business trying to simulate a microprocessor when you're dealing with hardware, and also when you're dealing with hardware that involves timing. And I'm guessing it's either a bug in that part of the software, or it's an oversight in my understanding of how to use it that I didn't take into account when I gave you the instructions. So, but I don't know what it ended up being. What would be interesting would be to try your code on an actual processor, though, and see if it works. And that would
buying one and making like a little binary to the decimal watch out of it.
Yeah, totally. Pick chips are cool. They're fun to work with. They're super powerful. They're very inexpensive. And I've actually been playing with one that's a mid-range device, an 18F45K22. It's a really, really sweet little processor, and but it's interesting to program because it's more complex than the one we use in 270 as far as some of the stuff we skip over, like the access bit. Well, that comes into play. So, but yeah, PICs are nice, Arduinos are nice, Raspberry Pis are nice. There's tons of good hardware out there to mess with if you want to sort of get your hands on the actual silicon and get down to sort of the lowest level you can without building your own circuits. All right, meanwhile, in the world of data structures, any questions so far?
I had one question about the first assignment.
Okay.
So, when we're adding items to our linked lists, and you mentioned auto sorting, do you mean sorting by the size of the data number? So like this node's number is 3 and this node's number is 4, so 3 comes before 4.
So I mean, sorting by the value stored in the data field.
Yeah.
Right. And we're going to talk about PA1 in detail, probably in the second half of today's lecture. So so you're a bit ahead of the game, but hopefully we'll clarify that and other questions about an hour from now. But yeah, for sorting, I'm talking about sorting by the value of data. All right, well, we were talking about arrays on Tuesday, and we discussed order of complexity. Let's see. $32W reg is cool. I don't even know how I would like manage that. All right, so talking about arrays, and you know, we can have an imaginary array, data bracket something, and we imagine it's got, you know, numbers like 12 and 22 and 11 and 18 and -5 and 101. And so we were looking at how much time it takes to do certain things to this array, and how that time is affected by the size of the array. So this is this notion of order of complexity, O of whatever. And so the first thing to think about is search. And if you want to search this array for a piece of data, there's really nothing you can do except, see if this is the data, see if that's the data, see if that's the data, kind of like move through and just check each element to see if that's the thing you're looking for. And if you have 100 numbers in here, it's going to take you, worst case, 100 checks to find your number or decide it's not in there. If you have 200 numbers in your array, it's going to take you 200 checks. So this is linear. This is what we call order n. And it basically means double the amount of data, double the time it takes. On the other hand, if you're going to insert something into the array, that's order 1. Because if I know my array has 6 things and I want to insert the number 17, I just go to the next spot in the array and I plunk a 17 down there. So that's super duper fast. And then delete, if we want to delete, for example, this 18, we can, just take that 18 and move the 17, the last number, into that spot. And so that's an order 1, but before we can do that, we need to find the thing we're trying to delete. So that's our search time of order n. And so this is not super impressive performance. I mean, an array is a very simple data structure, but order n is fairly unpleasant to work with. So any ideas how we could speed up the search time? If I was going to store a bunch of integers in an array, is there any way I can search for it more quickly than just going through all n numbers?
If you had a hash map where you put in the numbers associated with the index, so you just automatically jump there, assuming they're unique values.
All right, so that would work, but that's very sophisticated. That is something we're going to do later in the course. But without adding any additional data structures like a hash map, any other ideas? And we've done something like this in 224, although we didn't phrase it in these terms. But think back to some of your programming assignments in 224.
We can have an associative array, but that's just a hash.
That's a hash, right? Think about the high-low assignment. All right, someone said it in chat. So binary search. So when we play high-low, we're basically doing a search problem. One person is saying, okay, I'm thinking of a number between 0 and 100, and then the other person is doing a search to try to find what that number is. And if we take this approach, we'll say, is the number 0, is it 1, is it 2, is it 3, and it might take us 100 guesses to find that number. But if we think of this set of possible numbers as being sorted, what we can do is we can say, is your number 50? And they'll say, no, 50 is too small. Well, we've just eliminated half the numbers that we might have to guess. We don't have to guess anything between 0 and 50. We only have to guess between 51 and 100. And so now we'll say, is it 75? And if they say that's too high, now we only have to guess numbers between 51 and 74. So we're cutting in half the size of the problem each step. And so if we...
guessing game based off of that premise.
Yeah, that's a guessing game. And so if our data happen to be sorted and if this was what our data looked like and we were looking for the number 22, we could, start in the middle and say, is this my number? No, that's too small. So we'll only think about these and we'll pick a number in the middle, and maybe we pick 22 and there's your number, and it only took you 2 tries instead of 6. So these numbers are for just a bunch of data sitting in an array, no particular organization or order to them. But if we have our numbers ordered, our search time actually improves. And it becomes the log base 2 of n. It's the number of times we can divide the size of our data in half until we get down to just one piece of data. So yeah, this will be more computation, but it's a fixed amount of more computation. Whereas if n gets bigger and bigger and bigger, the advantage of log n versus n continues to get bigger and bigger. And no matter how much extra work it takes to do a binary search, if our data gets large enough, eventually the savings from that data set will outweigh the penalty of doing a binary search instead of a sequential search. And that's what the order of computation kind of tells us, is that as n grows to infinity, what's the term that's dominating our performance factor? Well, it's n. In this case, it's log n. And eventually log n times any constant will be smaller than n.
What would a sort be? So like, let's say we had the unordered array like that there, and we wanted to do the O log n search. Could we do like a preliminary sort first?
You could.
O log n?
You could do a sort first. If you did a bubble sort, that would be an order n squared, which would be unfortunate. If you do something like a heap sort, you can get down to n log n. If you do a radix sort, you can do an order n, but it's got a big constant in front. So ideally what we'd like to do is keep our array sorted at all times. So that, when the array is empty, technically that's sorted by default, but each time we insert something, we want to insert it in the right place so that our array remains ordered. And now we've got a problem, because if I want to insert the number 0 into my array, it's really got to go right here between the -5 and the +11. And there's no space for that in the array. The only thing I can do is move each of these things down in memory, and now I can store the 0 right here. And so our insert time goes up to order n, because we have to shuffle data around to make space for something new. And our delete time, if we want to delete the 17, we can't just move the last thing in the array up to that spot because it won't be ordered anymore. So we have to delete that by basically moving everything up in the array. And so this becomes order n. So what we're going to do is we're going to look at a different way to store something like a set of integers in order to improve these times. And we'd like to bring these back down to order 1. And when we do this week, our search time is going to go back to order n. But we're going to do this in a way that a few weeks later we'll be able to modify what we're doing this week and create what's called a binary tree. And a binary tree will be a way to bring our search time down to log n, and our insert and delete will also end up being log n. And so that'll get us to a really nice spot computationally wise. So the goal right now is improve our insert and delete performance. And so I want to take a look at the organization of arrays and think about, we've got a sorted array. And let's just suppose these things are stored in memory. And I'm going to suppose that it starts at location 200. And I'm also going to suppose that each integer takes 4 bytes to store. So this number 10 is going to be stored at locations 200, 201, 202, 203. This next number 20 is going to be stored starting at location 204, 30 at 208, 50 at 20C, and 100 at 210. So these are hexadecimal numbers. It's a good chance to practice hex. And if I want to insert the number 25, I've got a problem. If I'm going to go through my array and read out my data, I really need the 25 to come after the 20 if I want it to be in order. but my 20 is being stored at locations, 204, 5, 6, and 7. The next location in memory, 208, I've got a 30 sitting there. And there's simply no space between here and here to store my number 25. This is an important feature of arrays, right? With an array, if I want to access, data bracket I, that's at memory location 200 plus 4 times I. So data bracket 0 is at 200, data bracket 1 would be at 200 plus 4 is 204, 2, 3, data bracket 4 would be at 200 plus 4 times 4 is 16, that's 210 hex. So the fact that the data in our array is stored sequentially one after another and it's all jammed together as tightly as possible makes it really easy to access elements by just doing a little bit of arithmetic. Take the index, multiply by the size of the data, add that to the starting address of the array. That tells you where the data is stored. So that's a good thing, but it's a really bad thing for trying to shove something in here. So we're going to use a trick. We're not going to store our data in a simple array, but we're going to make a more complex array of sorts. And instead of just assuming that the thing after 10 is in the next memory locations, we're going to actually store something with a 10 which says where is the next number in this list of numbers. So I'm going to store a 10 here, and I'm going to say the next number should be stored at location 204. And at location 204 I'll find a 20, and I'll also put something next to that 20 which says the next number should be stored at location 208. And so on. And I can't do this with the addresses. I'm using all my bytes from 200 to 203 to store the 10. So I don't have space here to actually store the 204, but work with me on this. Just imagine that, somehow I can store 2 pieces of information here. Next to the 30, I'll store the location of the next thing, which is 20C. And next to the 50, I'll store the location of the next thing, which is 210. And what should I store next to the 100? Where should I say the next piece of data is? There is no next piece of data, so I've got to put something here which indicates that.
214.
I could put 214, but if I put a 214 and I was trying to pull the data out of my list here, then whatever was at location 214 would be considered the next thing in the list. And
0, right?
I don't want that.
0.
So I'm going to put a flag in there, and a really convenient flag is 0, because 0 is never a valid memory address. And so if I'm going through this and I'm pulling out the data from my list and I see a 0, I'm not going to go to location 0 to look for the next number. I'm going to see that as a flag and say, aha, there is no next number. This is the end of the list.
At that point, would you have to write a conditional, like if 0, then move on?
Yep.
Deal, or
Exactly.
okay.
Just
And-
like null terminator in a string.
And in C, we're going to use the word null, which is defined for us in an include file. And null is basically a symbol that means 0. But we're never going to look for a 0. We're always going to look for null. So basically, the things in our list are now composites. It's a composite of a piece of data and a pointer to the next piece of data. And so let me draw a slightly less fictitious memory map.
I have a quick question while you're doing this.
Okay.
On the last page, when you mentioned that an unordered array would have an O1 sort versus an ordered array would have an ON sort.
Sort or search?
Insert, sorry.
Insert, okay.
Sort. Why would it be a O1 insert on an unordered?
Because you can insert something into an array by just adding it to the end of the array.
Oh, so it's like an append. Oh,
Yeah, it's like an append, so we always keep track of the length. And so if the length is 6, I'll just store my new number at data bracket 6, and I'll change this to a 7. And it didn't matter if it was, 6 elements or 600 elements. It's still basically 2 operations to insert.
Okay.
All right, so let's imagine a list containing the numbers 10, 20, and 30. So, and let's suppose our list begins right here at location 200. So we're going to store a 10 here. And then in this next spot, I'm going to store, not a 20 yet, but I'm going to store the location where the 20 is stored. So I'm actually going to make my data look like this. And after the 10, I'm going to say, hey, the next number is at location 208. And at location 28, I'll store a 20. And the next spot, I'll say, hey, the next number is stored at location 210. And at 210, I'll find a 30. And the next spot, I'll say where the next number is stored. And that's where I'm going to store a null. So this captures this 3 sets of information in this given order. But watch what happens now. Let's insert a 15. Now with an array, I'd need to move the 30 and the 20 down in the array so that I have an open spot right here to store the 15. We don't have to do that. So I want to store a 15. I'm going to do 3 things. I'm going to find a new spot in memory that's not being used yet. And I'm going to put a 15 right there. I'm going to take the 10, and instead of pointing to the 20, which is 208, I'm going to point to the 15. I'm going to change this one field to say 10 is followed by whatever's at location 218. That's my 15. And then I'm going to say the thing after 215 is, in this case, 20, location 208. And that's it. I changed this number, I created this number, and bingo, I've inserted a 15. So how do I find what's in my list? I start off with a 10. I follow that to location 218. There's a 15, that's the second number. Follow that to 208. There's a 20, that's the third number. Follow that to 210. That's a 30, that's the fourth number. And the null says that's the end of the list. So now my list looks like a 10, followed by a 15, followed by a 20, followed by a 30. And if I want to insert, I don't know, an 11, 11 would have to go right here. I'd have 3 things I'd have to move down in memory normally. Don't have to do that. So I'll find a new block in memory. I'll store an 11. I want it to come right after the 10. So the 10, instead of pointing to location 218, is going to point to the 11. It's going to point to location 220. That's where I'm going to store the 11, and I want the 11 to point to a 15, which is right here at 218. So there's my data for this list containing 5 numbers with a 10, 11, 15, 20, and 30. Again, how do I go through this list and find what my numbers are? Start here, there's a 10, followed by 220 is an 11, followed by 218 is a 15, followed by 208 is a 20, followed by 210 is a 30, followed by null. That's the end of my list. All right, everybody got the basics set up?
I think so.
So let me switch modalities. And we're going to draw some pictures. And one of the most important things in a data structures course is getting good at drawing pictures. And the pictures that you draw to represent this will probably look different from the pictures I draw or the pictures that somebody else draws. It's an entirely personal preference. And when I first learned linked lists, my teacher drew pictures and they didn't make sense to me. And I started drawing my own pictures and they kind of made some sense and then they wouldn't and so on. But I eventually found a way to represent what I was thinking of here with a set of pictures. So if what I'm saying doesn't feel quite right, find a way to represent what we're going to do next in your own sort of graphical depiction. But here's how I think of what we just did. So this rectangle, represents these memory locations, a piece of data and a location where the next rectangle is stored. So there's my 10, and there's my 20, and there's my 30. And I'm going to draw arrows down here that basically point to the next block. And the idea is, the part of this node, this is the data part, the other part that tells me where the next thing is stored, well, it's actually an address, right? It's a big long number that corresponds to a location in memory. 220 is this location in memory, that's where I find the next number. I'm just going to depict that with an arrow that points to the block stored in that next chunk of memory. And down here on my last node, I'm just going to write null to say that's the end of my list. So there's our original list containing a 10 and a 20 and a 30. And now when I wanted to insert a 15, I make a new block 15. I have my 15 point here, and I change this pointer to point to the 15. And now that's what my list looks like. And then when I add a new node, go ahead.
Pretty similar to the one I ended up drawing for myself.
Awesome. And then when I insert the 11, I'm going to have this point to the 15. And I'm going to take the node before it and change that to point to the 11. So now it's a little easier to see what our list looks like. If we know we're starting at a 10, 10 is followed by 11, is followed by 15, followed by 20, followed by 30, and that's the end of the list. 10, 11, 15, 20, 30. All right, so this is another way to think about storing this information. So let's think about algorithms. We can do this on paper, right? I just kind of said, let's find a new piece of location here, and I want this to come right after the 10, so I changed that. But how could we tell a computer to do this? Because a computer doesn't have a piece of paper in front of it. Let's suppose we want to insert an 18. So we know that we want to make a new block, and we're going to store an 18 in the data field of that. But the trick now is figuring out where we're going to store this in our list. So here's what we do. We start with the beginning, and we're looking for the first number that's bigger than 18. All right, so we'll look at a 10, that's smaller. We'll follow that to an 11, 11 is smaller. We'll follow that to a 15, 15 is smaller. We'll follow that to a 20, 20 is bigger. So we know that we want to insert right before this node, but right after this previous node. And so we're going to remember, as we're going through looking for the first number that's bigger than what we're inserting, we're going to remember the previous node that we saw. So that when we find the 20 and we say that's the first number that's bigger, we also know what the node was right before that. And we need both of these. And so now we have to do two things. We have to take our new node and point to this node that's bigger. So change this to point to the 20. And then we have to take the previous node and point that to our new node. And that's all we have to do to insert. Make a new node, march through the list, find the first number bigger than what you're inserting, change your new node to point to that, and change the previous node to point to your new node. And we'll repeat that probably like 20 times over the next week. But now the effect is 10 points to an 11, which points to a 15, which points to an 18, which points to a 20 and a 30, and that's the end of the list. So questions about that?
So the only penalty is extra disk space, right?
Yeah, you're using more than twice as much disk space, because these pointers actually need, at least 4, probably more like 8 bytes for each pointer. Our integer only takes 4 bytes maybe, and there's extra padding, so we're going to end up using about 4 times as much memory compared to an array. But it's going to be worth it in the end. Memory is cheap, time is priceless, basically.
Isn't it a problem to like have to lock all those pointers sometimes though?
To do what?
Like if you needed to search through a linked list like this, you would have to lock the pointer X amount of times to search for something, right?
Yeah, so to do a search, we have to do an order n operation. We can't do our high-low game on this. So starting at the beginning, if we're looking for a 30, we're just going to have to go no, 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 no. Yes, there it is. But we're gonna fix that problem in a couple of weeks when we talk about binary trees. All right, let's see. Someone said when I took a data structures course before, we started with stacks, lists, recursion, and then linked lists. Why do you start with linked lists? I'm starting with linked lists because it's a fairly low cost way of getting deeper into pointers. And even though we touch on pointers in 121 and we use them in some cases in 224, pointers are still fairly mysterious by the time most people start 222. And I want to get an early start on that, and linked lists are kind of the gentlest data structure I know of that forces you to use pointers, but isn't too horribly demanding after that. And I don't even touch recursion until we get into trees, because I want to motivate that in terms of how we're going to use it instead of introducing it on its own. But if you've done 215 or you're doing 215 now, we actually deal with recursion in there when we get to proofs and mathematical induction. You can also make it doubly linked. Yes, we can do all kinds of variations on this. Eventually we'll talk about doubly linked lists where we also point backwards, and circular lists where the last node points back to the first, and so on. So this is a very rich set of data structures. All right, let's talk about deletion. So suppose I want to delete my 15. Really, all I've got to do is, right now my 11 is pointing to the 15, and my 15 is pointing to the 18. I'm just going to change my 11 to point to the 18. Bingo, my 15 is gone. It's a super simple operation. In what sense is my 15 gone? Well, if I start with my 10, that takes me to 11. 11 takes me to 18. I skipped over the 15. So 15 has been deleted from the linked list.
So it's deleted from the list, but it's not deleted from memory.
Exactly. And that's an important thing to keep in mind. When we remove something from a data structure like this, we don't necessarily remove it from memory. Just like when you delete a file on your hard drive, you're basically removing that file from a data structure called a directory structure, but that file is still on the hard drive. Unless you use something like a shred program, the bytes that were contained in the file are still on the hard drive in the same spot they were. And this is why you can undelete files if you accidentally delete them. This is why people recover, incriminating information that someone tried to delete from their hard drive but didn't shred. So this is important security-wise. If you're using a linked list to store, authentication information or credit cards or things like that, and you were to delete a node from the list, that node is still in memory. And those bits are still out there, and somebody could snapshot memory and retrieve this information. So you might want to scrub it, replace it with, some other bit pattern or things like that. So yeah, like the recycle bin on Windows. But ignoring those concerns, deletion, very, very simple. Just change your pointer. So let me draw a simpler view of a list. There's our 10, 20, 30. If we want to insert a 15, I'll change my 10 to point to the 15, and my 15 to point to the 20. If I want to insert an 11, I'll change my 10 to point to an 11, have 11 point to 15. Now if I want to insert an 18, I'll change my 15 to point to the 18, and 18 to point to 20. So what's in my list? 10, 11, 15, 18, 20, 30. And I'm usually not going to, draw an arrow that points to null. If I don't have an arrow, I'll just take that to mean that the pointer there is null. That's the end of the list. And so how did we delete our 15? We changed this 11 to point to the 18. So 10 goes to 11, 18, 20, 30. Yeah.
Let's say you have this kind of list, and you have, let's say, just as much memory in the background because things are hovering and aren't connected to these nodes. Would you just run maybe the occasional thing to just look for things that aren't connected to nodes to delete that stuff?
That's an excellent idea, and that's actually what some systems do. They have what's called a garbage collector. And the garbage collector's job is to go through and look for, here's a 15, nothing is referring to it, I'll reclaim that memory. So Java, for example, has a garbage collector, so does Lisp. In C, we don't have that, so what we're going to do is when we delete that 15, before we're done deleting, we're actually going to tell the operating system this block of memory is available now. And so we're going to call a function called free, and it's sort of the counterpose to malloc. We're going to use malloc to say, hey, I want some memory. We're going to use free when we're done with a block of memory, and that'll return the memory to what's called the heap, the pool of available locations.
So you wouldn't want to do linked lists on the stack, you'd want to only do them on the heap for that reason?
Yeah, it would be a little tricky to do on the stack because you'd probably end up wasting that space when you delete, because stacks are, necessarily last in, first out. But the heap, we can just, grab memory from all over the place and we can return it and still make use of it.
We can also make destructors. It's free too, right?
In what sense?
If we wanted to get rid of some, we wanted to remove the entire linked list, we could have some sort of function that frees up all of those bytes.
Right, and that's going to be part of PA1. You're going to write a function to do exactly that, which will basically go through all of the stuff in the list and release all that memory. So we'll talk about specifics for algorithms to do that. So the main thing we're going to be doing in all of this code is start at the first node and then follow the links. Right, assuming we know the list starts here, we're going to do whatever we want. If we're searching for a number, we'll compare. If we're trying to find a place to insert, we'll do a comparison. If we're printing, we'll do a print. But we're going to do something with a number in this first spot, and then we're going to follow its link to the next thing in the list. And we'll do whatever we're supposed to do with the 11, and then follow the link in that node to the next thing in the list, which now is an 18. And we'll keep doing that until We're ready to follow the link to the next node, but the next node says that it's null, and that's going to tell us, oh, we're at the end of the list. So you'll hear me talk about, following the links from node to node. That's the basic process, and that's what we keep doing on paper here.
Would there ever be like a reason to, let's say you have a linked list and you want to avoid, you might need to start searching the structure quite a lot.
Mm-hmm.
So would you ever like have an instance where you would convert a linked list to an array because you need to constantly search that array and it's fast to do so?
You could. You could go through your list once and save the data in an array, and then you could play high-low. Because arrays, we have this ability to use an index to go straight to any spot in the array. But the more likely resolution would be to, instead of using a linked list, use what's called a binary search tree. And a binary search tree will be a linked list with extra pointers that point to sort of the midway section of the list. So if you want to look at a number in the middle of the array, the list, we can find a pointer that goes right there. And it'll bring us back to this nice log n performance. But you could throw it into an array and use an index also if you only wanted to do that once. That would be a good solution. All right, so we have a potential complication if we're trying to do things related to the first node. And by node, I mean, the number plus the pointer to the next thing. So let's suppose our list looks like this. And I keep saying, you have to know where your list starts. Your list starts, in this case, right here on the 10. So you've got some variable in your main program that says, this is where my list begins, and it points to that first node. But here's a potential problem. Suppose I want to insert the number 5. Well, I'll start at my list and I'll find the 10 and I'll say 10 is bigger than 5. Remember, I'm looking for the first number bigger than what I'm inserting. That's right here. And I said you need to know what the previous node is so that we can adjust that to point to our new number. Well, there is no previous node here. The first number in the list is bigger than what I want to insert. So really what I need to do is I need to put a 5 and have it point to the 10. But unless I'm very clever, my main program still thinks the list begins here. And it's not going to see that 5. I would need to somehow tell my main program and everybody else using the list, hey, forget what you knew a minute ago. The list does not begin here. The list actually begins here. And that's a bit of a problem. In C, it's a little challenging to sort of change the value of a pointer that's given to you. We get into like double stars and all this kind of stuff. So that's one issue. The second issue is, if we're back here, we've got a list 10, 20, 30, and the person decides to delete the 10. Well, there's no node before this that we can say, hey, you should point to 20 instead of 10. And really the only way we can delete the 10 is, again, to tell the main program and everything else using the list, hey, this is now the first thing in the list. And that's also a little quirky. So we have these special processings that need to happen if we try to insert before the first node or we try to delete the first node. And also, if we decided to delete not only 10 but also 20 and 30, what does our list look like? Well, it's, an empty spot on a piece of paper. There's no nodes. And now my main program, I have to tell it somehow, if you want to do anything with this list, just don't. Because the list has no data in it. And that's another edge case. So we're going to use a trick. We're going to use a trick to eliminate all of these edge cases in one fell swoop. And that trick is called a sentinel node. And the sentinel node is a really, really simple idea. We start our list with sort of a dummy node, a placeholder called S. And, if my list contains a 10 and a 20 and a 30, this is what it actually looks like. And I tell my main program, this is the beginning of my list. But all my code knows this is not actually part of the list. This is just a placeholder node in the beginning that points to the first node. And so we do one extra step in all of our code. We skip over this first node. But now there's no special cases because we never actually do anything with the first node of the linked list. Worst case, we do something with the second node. And so if I want to insert a 5, what do? I make a 5. I take the previous node, which is the sentinel, point to the 5, and I have the 5 point to the 10. And if I want to delete the first node, I just change the sentinel to point where that first node is pointing. And if I want to delete the 10, I'll change the sentinel to point to the 20. And if I want to delete the 20, I'll change the sentinel to point to the 30. And my algorithm is exactly the same, whether I'm deleting something halfway through the list or something right in the very beginning. And if my main program looks to see what's in the list right now, it's going to start at the sentinel, see that it points to a 30, it's going to say you got a 30, and 30 points to null, so that's it. And if I want to delete the 30 and have an empty list, I'm just going to change my sentinel to point to null. And my main program still knows where the sentinel is stored, and when it calls the print routine to print the data, it's going to start off here, look to see what the first node is, and see a null and say, oh, there is no node, I guess the list is empty, and it'll just return. So we're going to use sentinels in our linked lists.
Quick reference question.
Mm-hmm.
This sentinel, this is basically an item that we're forcing into the list, but that will not show into the list. That way it just exists constantly.
Exactly.
Okay.
And it spares us from ever having to actually delete the first thing in the list or insert before the first thing in the list or have a list that has no nodes at all. Alright, so let's look at one more view of a memory map. And I'm going to do, the simplified view we started with, or I'm just going to assume that, my integer and my pointer are stored in each of these regions. Instead of staggering them out, and so let's suppose our sentinel is at location 100, and we want to put a 10 into our list, right? So we're going to look through our array, and the sentinel is referring to null, so we know our list is empty. So we're going to find a new spot in memory. Let's say it's this spot right here. We're going to put a 10 in there. We're going to change the sentinel to point to that node, and we'll have our new node point to null. So our list looks like this. And let's insert a 30. So we'll find a new location in memory, we'll put a 30 there. We need to find where to insert it. So we'll start at the sentinel, follow that to our 10. 10 is not bigger than 30. But that's the end of the list. So we know 30 should go at the end of the list. So we do two things. We take the last node in the list, which is 10, and we point that to our 30. And we change our 30, and we point that to null to say that's the end of the list. So now our list looks like this. And now let's insert a 20. So we'll find a new spot in memory, put a 20 there. And now we're going to find where to insert that. So we're going to start at the sentinel, see what that points to. It points to a 10. 10 is smaller than 20, so we're going to keep going. Points to a 30. 30 is bigger than 20. We want to insert right before this node. So we're always going to remember the previous node, which is a 10. And now we're going to do two things. We're going to change our new node to point to this current node, right, the 30, which is at location 108, And we'll go back to the previous node, which is right here, and have that point to our new node. So this will point to 10C. So what's our list look like? The sentinel points to 104, which is a 10. The 10 points to 10C, which is a 20. And the 20 points to 108, which is a 30.
Can I ask a devil's advocate question?
Absolutely.
What about duplicate numbers?
Well, so I did not disallow them in the programming assignment, but your main program will prevent duplicates from occurring. But if you have a duplicate, it doesn't really break anything, depending on what you want out of life. But you know, if I were to insert another 20, I would probably come down here, and when I got to this number that was, you know, bigger than or equal to what I was inserting, I would just insert right before that. So I'd squeeze another 20 between here and there. And it doesn't really break anything. And then when I delete, you know, I'll find the first number that matches the thing I'm deleting, and I'll change the previous thing to point where that thing is pointing. And so I don't think it causes any problems. So now we can start to sketch out a little algorithm. Let's suppose we want to insert a number n. So we're going to start at the sentinel. We're going to follow the links until we find a node with a data value bigger than n. And as we're following the links, we're going to always remember what the previous node is. And that's probably the trickiest part about doing an insert. Everything else will be pretty straightforward once we look at some code, but as we're following the links, we need to sort of remember where we were one spot back, so that when we find the spot where we want to insert, we know the previous node. So now let me put a comment in my pseudocode which says insert between previous and the current node, the node that we just found. So let me just call this node current. And we want to insert between previous and current. So how do we do that? Make a new node. Which I'll call new. Set the data equal to n. Set the pointer to the node we want to insert right before, and then set the previous node to point to new. So let's run this algorithm through when we say insert 15. So n is equal to 15. We're going to start at the sentinel. We're going to follow the links. And as we follow the links, we're going to think of the node that we're looking at as our current node, and we're going to think of the previous node we were looking at as previous. And we're looking for a place where the current node's data is bigger than 10, bigger than 15. Okay, that's not the case here, so we're going to follow the links. We're going to say, well, this points over to here, so this is going to be our current node. This is going to be our previous node. And we're going to look at this node's data, which is 20. 20 is bigger than 15. So we want to insert between previous and current. We want to make a new node right between here and here. So create a new node. Let me call this new. Set the data value equal to 15. Set the pointer here to point to current. So that goes there, and set the previous node to point to new. And there we go. All right, draw pictures before you start trying to write code. Don't even open VI with the idea of writing code for this until you've drawn a bunch of pictures showing these operations. You've got to be absolutely crystal clear in your own mind what you want your code to do before you start writing the code. That may seem obvious, but it's so common for students to start trying to implement something like this without actually understanding what they're trying to do. They're trying to implement what they saw me do in class, or what they heard somebody say in a YouTube video, or what they read somebody said in Stack Overflow, right? Make sure you understand what you want your code to do. How do you want these little rectangles and arrows to change? Once you understand that, writing the code will be trivial, right? We're going to have to talk about the mechanics of it, and you're going to have to get some practice, but actually writing the code will be very straightforward. The real challenge is understanding, what do I want these blocks to do? Where should the arrows point? How should I find the right block? So draw lots of pictures, work through this, right? Work through this with friends if you like. And then when you understand the steps that you want to follow, something like this, then we can talk about how to write code to do it. And we'll start looking at some of that code in a little bit today. But it really won't get you very far until you're totally clear what you want to do. So this is how we insert. Deleting is pretty much the same, right? Start moving through, find the first node that's equal to the number that you want to delete. And then when you get there, change the previous node to point wherever that node is pointing. So if I'm trying to delete the 20, come down here to the 20, that's the node I want to delete. Change the previous node to point wherever the 20 is pointing. That'll put an arrow from the 10 to the 30. And now the 20 is deleted. And so we'll do all these things multiple times over the next few weeks. But this is kind of a first pass through the higher level algorithms. All right, so let's do a 5-minute break, and we'll come back and we'll take a look at programming assignment 1, and then we'll start digging into some code. So I'm going to go 14:10. We'll do a 5.5-minute break. All right, so I'll be back in a few.
usually have the TV on and I can tell it's you and I'll hang up my other call and call you back. So that's all. I'm fine. I'm glad to hear from you. Hope everybody is okay. Oh, the message. Message erased.
All right, welcome back. So let's start talking about PA1. So this is your first programming assignment for the course. It's due a week from tomorrow at 8 a.m. So make sure you know the submission time. 8 in the morning will be the usual for our programming assignments. And so this is an exercise in implementing a linked list in C. And there's going to be two pieces to it. You're going to write the code to create a linked list, to do inserts and searches and deletes and prints and all that kind of stuff. And then you're also going to write a main program that lets the user, that's me, exercise your linked list and play around with it, add things into it, print it out, delete them, and so on and so forth. And you can also use this main program, to test your list code yourself and make sure that it's working, it doesn't throw seg faults or hang up or things like that. So let me go through the details of this, and then we'll come back and we'll start talking more about specifics related to coding. So we're going to use a structure, right? Each of these blocks is going to be, one number in our list, but it's more than just a number. It's a number plus something that tells us where the next thing in the list is. And so that's going to be a structure in C, and it's going to be a structure called myNode, and it's going to have two fields to it. The data field is just an integer, but it's also going to have a field called nextNode, and nextNode is a pointer to a struct myNode. So here's one of these things where if you think about it too deeply, you'll get brain locked. And it's sometimes beneficial to not think too deeply about what these things do and to wait for that understanding to come later. But from looking at this, it looks self-referential. It looks like this thing is pointing to this thing. But that's totally okay. That will not confuse the compiler. If I didn't have that star, the compiler will complain about a circular reference. But all I'm saying is this thing down here that I call nextNode is a memory address. And by the way, what I find that memory address is going to be one of these structures. But to the compiler, all it sees is I've got an integer and I've got a memory address. All right, so data is the number. Go ahead.
So all the structures are going to be struct myNode?
All the structures for the linked list, yes.
Okay. They'll just have their own data and obviously their own pointer to the next one.
Yep.
Okay.
So each block's going to have a number that's in the data part, and then it's going to have a pointer to another node, and that's going to be the next node part. And that'll be null at the end of the list. So next node is the memory location of the next element, or null for the end of the list. And you're going to need a sentinel node. So your main program needs to know where your list begins, and that's going to be, something that gets fixed in the beginning and never changes. It's got to have a handle to the sentinel node. And so that sentinel is going to be a struct myNode star, a pointer to a struct myNode, and you can call your sentinel mylist. And if we wanted, multiple linked lists, we could have multiple sentinels, each corresponding to a different linked list. So I want you to call the list in your program mylist. All right, so you're going to implement 6 functions. And as part of implementing these, you may create new functions on your own that these will use. That's totally fine. but you need to have at least these 6 functions. And the naming and behavior of these has to be exactly what's in the specification. You're going to lose 35 points out of 100 if you deviate from this. So it's really important to follow the spec, because I'm going to link your functions into a different piece of test code. And if you call this init with an uppercase I or something, nothing will link, code won't run, you're going to lose a bunch of points. So make sure you follow this spec. So your first function is called init. All that init does is create a sentinel node. So how does it do that? It calls malloc to create a struct my node. It should set the next field to be null, to say, hey, there's nothing after this, it's an empty list. And it's got to set the data field to be 1, 2, 3, 4, 5, 6, 7. Right? Now we never use the data field in the sentinel node. If this is the sentinel node, we never print out the value there. We use the sentinel to find what the first node is in our list. But I want you to load this magic value 1, 2, 3, 4, 5, 6, 7 into the sentinel. And now when you're running your code, if you print out your list and you happen to see this number pop out, you know that you're accidentally doing something with the sentinel that you shouldn't. So that's all that init does, and it returns the address of the sentinel node. So it returns a struct my node star. All right, the add function. Yeah, go ahead.
Do you have, in my program, I put like the struct definition and the prototypes in like a linked list.h. Is there any like specifications on the file name?
Yeah, we'll get to that, but it's going to be called main.h.
Okay.
All right, so the add function is used to insert into the list. So it takes the sentinel node, right, which is a pointer to a struct my node, and it takes an integer that you want to insert. And it does the thing that we've done a few times now. It starts at the sentinel node, follows the links to find the first node bigger than number, and then it inserts a new node containing number in between the previous node and the current node. And this function should generally return 1 unless it fails catastrophically. The only way this can fail is if it runs out of memory. So when we use this malloc function to ask for a new location in memory, it's possible that malloc will tell us, hey, there's no memory left. If that happens, our program is probably not our biggest worry. Probably our machine is crashing. But if that happens, your code should return a 0, saying I was not able to add your number. All right, print, all it needs as an argument is the sentinel node. So you call print and you pass it my list, and that should print out the data values for all the nodes in your list. So again, starting with the sentinel, it's passed as an argument. Go to the first node, print the data value. Follow the link to the next node, print the data value. Follow the link to the next node, print the data value. Try to follow the link, but notice that it's null, and so that's the end of the print routine. And you're going to want to print all your numbers on one line separated by spaces, and then when you get to the end, print out a new line. All right, delete is like add, except it deletes from the list, and that returns a 1 if it succeeds and a 0 if it fails because the thing you wanted to delete wasn't in the list. So if I tried to delete 11 and 11 is not in the list, delete should return a 0. And then search takes a sentinel node and a number, and it looks for that number in the list. It returns 1 if it's found, 0 if it's not. And other than print, these functions should not print anything. Don't ever send output to standard out unless you're told to. If every time I call search I get a message on my screen that says, I found the number, I'm not going to use your code. Because, maybe I'm writing a web server that's going to do 1 million searches a second, and your code's sending 1 million print messages to my console screen every second, right? That's not what we want. So don't produce any output unless you're told to produce output. Now when you're debugging, when you're developing your code, yeah, put in a lot of output. Do a lot of print statements. Let yourself know where you are. But make sure the final version that you turn in, the only time you're printing anything is from the print method. If you try to delete a number that's not found, don't print a message saying number not found, just return a 0.
So we should use those return values for just making sure it was successful or not.
Yeah, now your main program is going to be very chatty. In the main program, if the user says delete 11 and 11's not found, your main program needs to tell the user, hey, I didn't find 11. But how does the main program know that? Because it's going to call delete, and it's going to check the return value and see that it's a 0. That's how the main program knows, oh, 11 wasn't found. So now that will have a print message that says, hey, you know, you tried to delete a number that didn't exist.
Okay, perfect.
Cool. All right, and then cleanup is this thing that gets rid of all the memory that you've allocated. And we'll talk about how to do that, but that's going to be using the free method, the free function to undo what you did with malloc. And what I'm talking about here, this paragraph, is a key concept, which is related to something we call abstract data types. So throughout this course, we're going to be talking about data structures. We're going to talk about linked lists, doubly linked lists, circular lists, hashes, stacks, queues, binary trees, search trees, tries, heaps, all kinds of data structures. And we're always going to describe, you know, what we do with these data structures. So for example, with a linked list, we add, we delete, we search, we print, we initialize, we release from memory. The way that we implement a linked list should not affect the way that you write your main program. When I'm writing my main program and I'm in the section of code where the user has asked me to look for a number, I should call the search function, give it the sentinel node, give it the number I'm looking for, look at the return value. If it returns 1, I'll print something like I found your number. If it returns 0, I'll say I didn't find your number. If somebody comes along and rewrites the search function to do some totally different implementation of a linked list, that should not change how my main program uses this. So we're thinking of kind of firewalls, right? Here's your main program, or the user, and here's the linked list implementation. And, you know, there's communication between these, but this communication is very, very strictly defined and very tightly controlled. And in our case, the interface between the main program and the linked list is these 6 functions, and that's it. So your main program should never, ever, ever call the malloc function. Your main program should never, ever look at, you know, some node's next node field or some node's data field. It should never monkey around with the way that the linked list is implemented. The struct my nodes, the next node field, the data field, the fact that there's a null at the end, the fact that there's a sentinel in the beginning, all of that is invisible to the main program. For example, we're describing linked lists that have sentinel nodes, but we don't need a sentinel node. We can write a linked list without a sentinel. We just have to do some extra stuff. We could make a linked list that was doubly linked, even if we're not using the backwards links. We could implement a linked list by having something that calls somebody on a desert island and reads them a text message saying, hey, insert an 11 into this list. And they could, you know, scratch with a stone on the side of a coconut the number 11 and draw some new arrows. And our main program should still work exactly the same. Might be a little slower in that case. But we don't have to change the code. But if we write our main program and we say, okay, let's look at sentinel.nextNode.data and see if that's equal to the number we want, we're violating this firewall, right? We're not writing our main program to interact with an abstract linked list. We're interfacing with a particular details of our linked list implementation. So as long as your main program only uses these things to interact with a linked list, you're set. But if you find your main program calling malloc, calling free, looking at next nodes, looking at datas, that kind of stuff, then you're probably violating this firewall. Okay, so this is a general concept. We'll push this a lot in 223 when we do object-oriented programming. Most of what we do in something like Java is dealing with structures as abstract data types. And it means that, you know, if the implementation of the data structure changes, our main program still works. And that's really important.
So in this case, the main program should basically just see what the user wants to do and then call on those functions, basically.
Exactly, yeah. The main program will take input from the user, figure out what they're asking to be done, and then it will call these functions to do that. All right, so again, each element in the list will have two fields, a data field and a next node field. Here's a rehash of the algorithm we've been using to add a number to a list. Right, create a new node with the desired data value, search the list for the proper point to insert, adjust the previous node's next node to point to the new node, and have the new node point to the next node's the next node. All right, anytime that you want a new node, we're going to use malloc. We're still going to do some code today. We'll use malloc. How many bytes do we need? Use size of struct mynode to figure out how many bytes. Don't try to add them up yourself because it will vary from system to system, from year to year. But size of struct mynode will always tell you how many bytes you need for a struct mynode. And don't do a struct mynode star. We're not using a pointer as a node. We're using a node, a struct mynode. So we need to know the size of that whole structure to tell us how many bytes to get. Thank you. And then we're going to use free to release memory, and we'll see how to do that in a bit too. All right, so that's the linked list side. The main program, there's a sample main program you can play with to see these details, but pretty straightforward interface. So you run your main program, first thing it does is print a prompt. And I don't want to see any other introduction, any other wordage or anything like that, just print a greater than sign, that's your prompt. And you're waiting for the user to type a command. And there's only a few commands. They can say insert a number, which is I followed by an integer, I space followed by an integer. And print success if you manage to add that number. But if the node is already in the list, print out an error message, node already in list. And if you happen to run out of memory, say out of memory. And the way that we're inserting, where we say find the first number that's bigger, that's going to guarantee our list is always sorted. So now when we say print, which is the P command, we'll print out the data in our list in order, and again it comes out all on one line separated by spaces.
And so when we're starting our program, we're going to assume the user knows all the commands.
Mm-hmm.
No, nothing like this. Okay.
Yeah, you can assume they're a very sophisticated user. All right, so
the normal case, right?
right. So you can say S space number to search for a number and report either found or not found. Say D number to delete a number and either say success, or if the number is not found, say node not found. And then X lets you exit the program, and that should also free all the memory. If you type in anything else, if you don't put in a legal integer after this and so on, print out a short help message. Alright, so there's sample code on the Linux server that you can use to double check what we want this to do. So there's our prompt. If I say insert 20, insert 10, it says success. Insert 20, success. Insert 15, success. I can say P to print the contents of my list. So there we go, 10, 15, 20. And it's all nicely sorted. I can insert a negative 100, that goes in the beginning. I can insert a 2000, that goes at the end. If I try to insert a number that's already in there, my main program should search first, and when it finds that the 20 is already in there, it should not insert it again. It should print a message saying node already in list. If I put in a 21, that should be fine. I can search, so I can search for a 20, that's found. I can search for a 33, that's not found. I can delete my 20, that's successful. If I delete a node that's not in there, it should say node not found. And that's pretty much it. So error checking, if I just say I, that's not valid. It's got to be followed by an integer. If I say I haha, that's not valid. If I say I 2.3, that's not valid. If I say I 2.3, that's not valid. It's got to be I space followed by an integer. That's valid.
So we're going to want to use scanf then.
Yeah, you're going to want to use scanf with that %s for the extra thing and all of that business.
Okay.
And I'm not too worried about this. The main program is only worth, a small part of the grade. But I want you to keep the good habits from 224 as far as parsing input and so on and so forth. And then the X function will take me out of the program. All right. So run the sample executable. If you have any questions about, what should my program do in this case, you can try it in here, and that should tell you. Coding style. I'm not going to impose a particular coding style on you, but I do want you to have a consistent coding style. Meaning, how you indent, where you put your curly brackets and conditional statements, how you nest, and so on and so forth. Hopefully most of you have already developed, your own style for this. Just keep using that. I'm not going to put any particular requirements on it, but have consistent indenting and so on. You need to comment your code thoroughly. A lot of what we do in the programs that we're going to do in this course will have, 1 or 2 lines of C code that are making some major change to the underlying data structure. And if you came back to this code 2 years from now and you just saw, this line of C code that says, this thing arrow, that thing dot this equals this other thing, you're probably not going to have any idea what that statement is doing. So what you want to put in your comments is why you're doing whatever you're doing. Right? So if I say, new arrow next equals temp, don't write a comment saying set new arrow next equal to temp, because I can see that from the statement. But why am I saying new arrow next equals temp? Set the new node's pointer to point to the node that we just deleted, right? So explain why you're doing each statement, why you've written each statement, not what it does to the computer. Because if you know C, you can read a statement in C and know what it's going to do. But why? You want to explain the whys. All right. You want comments in the beginning of each function describing what the function does. So for example, the add function, don't just say adds a node to a list. The add function, you might say something like, take a sentinel node to a list and an integer and insert that integer into that list. The integer is inserted so that the list remains sorted from smallest to largest. The function returns a 1 on success, 0 if it runs out of memory. Note, if you insert a node that's already in the list, this does not cause any problems. Or this causes my program to blow up. Or whatever, right? So you want to describe all the details of the function so that somebody who wants to know these details does not have to read your code and reverse engineer it. So at the very least, you want to describe what the inputs to the function are, what the return value from the function means, what the function does, what assumptions you're making, what assumptions you're not making, what error conditions could occur, and so on and so forth. So really think about how you can describe these functions. And it's not a bad policy to write those kinds of comment blocks before you begin writing the code, because it will help you make sure that you're writing your code in a way that corresponds to what the assignment's asking you to do. So blocks inside the beginning of each function. Block of comments in the beginning of main.c, which describes, should list your name, the date, the class, and a detailed description of the program. Okay, something more than just linked list program or PA1 or CSE222 assignment, right? What does it do? And put it in your own words. Don't just copy and paste from the assignment prompt. But think about what the program does, all the aspects of it, and put a comment block in the beginning of main.c that describes that. All right, Program structure. Your program has to break into 4 nice, neat, clean pieces. The first is main.c. That's your main program, including any functions that your main program needs that you're writing. Not the linked list stuff, but if you're going to write a function called parse that takes the input from the user and decides what they're asking you to do, put that inside main.c. Functions.c includes these 6 functions and any other functions that these things use. So if I have a function called, make a new node, I would put that in functions.c. Main.h, which has the structure for my node and all of the function prototypes. Okay, so main.h describes what a struct my node is and lists all the prototypes. And the idea is I'm going to have my own main program that I'm going to test your linked list code with. So to compile my main program, I'm going to include main.h, so I know about your function prototypes, and then I'm going to compile it with functions.c. In other words, I'm going to have my own main program that replaces main.c. And I'll link that in with your linked list, and I'll run my code and exercise it. But you're also going to give me your version of a main program, which is main.c, functions.c, main.h, and then a makefile. And as with 224, this has to be a proper makefile. So it should compile things to objects, it should link the objects together, and it should only compile things that have changed. So don't just write, a one-line makefile that GCCs everything in the universe. Make it tactical. And also make sure you include a clean option, which removes the objects and the executable. Alright, submission. Again, we're not doing Git this quarter for submission, so you're going to submit through Canvas. You're going to take your 4 files, and you're going to turn them into a tar file. You can use this command exactly as it is. tar cvf pa1.tar, and then list those 4 files. Once you have a pa1.tar, upload that to Canvas. So go to the assignment for pa1, there'll be an upload button, click on that, drag the file or specify it into the File Explorer. If you have not done tar, or you haven't done it in a while, make absolutely sure you know how to use tar before you get to the end of your assignment and you're ready to submit. Tar is one of these commands that can easily corrupt your files. And every time that I have students submit through tar, there's always a handful of students who send in their tar file, and when I try to extract it, their files are corrupted. They're filled with binary. And it's because somewhere along the way they misused the tar command. So make sure you've got backups. Make sure you're using something like Git to save versions of your code. Make sure you've got backups of your backups. Make sure you've got things stored off of your hard drive, right? And then when you're ready to create your tar file, right, make sure you've already practiced this. Practice it, in the beginning of the assignment rather than at the end. Practice on junk files. If you're doing this on the Linux server, and you want to make sure that your code runs on the Linux server, right? If you're doing this on the Linux server, you need to get that tar file to your machine so you can upload it to Canvas. If you're on Linux or OS X, you can use SFTP. If you're on Windows, you can use WinSCP, which you can download. It's similar to PuTTY, and it's a drag and drop between the server and your local drive. Alright, so grading. A few points of deduction. So if there's no submission at all, if your tar file is corrupted, if, main.h is missing, and so on, it's 100% deduction. Right, so make sure all those pieces are there. Make sure that the makefile builds your executable. If your code doesn't compile, if I say make and it gives me some sort of syntax error, or I try to run your program and the first thing it says is seg fault, right? That costs you at least 50 points. And I will go in and I will see if there's an easy way to get your code to run. So for example, maybe you added comments at the end, and the last thing you did was add a comment with your name, but you only typed 1 slash instead of 2. Well, if your program begins with a single slash, it will not compile, right? So if I go in and I see something like that, I'll fix the problem, I'll recompile, and I'll go ahead and grade the rest of it. But you'll still lose at least half credit. And these things are easy to avoid, right, by just double checking what you're submitting before you submit it. If you don't follow the exact function names, the exact function prototypes, the exact struct mynode structure, and so on and so forth, that's 50 points off. And that's because I need you to follow that specification so that I can use your linked list package with my own code. And this is super important, you know, if you're doing group work, if you're working on a larger project, if you're working in, you know, industry and you're developing some piece of a larger project, right? You're going to have to follow a spec that says, here's the functions you're writing, here's their names, here's what types of arguments they take, here's what the structures are, and so on and so forth. And if you don't follow that spec correctly, then other people down the line, their code's not going to work. And they're going to come and get upset with you and take away your cappuccino and all this stuff. So this is really important skill-wise to develop. And then the other thing is this program has to be split into these 4 pieces: main.c, functions.c, the include file main.h, and then a make file. So that's 35 points off if it's not set up that way, because I'm going to have to go in and like break it up myself. All right. Assuming we've gotten through all of those, you get points as follows. Proper makefile, 5 points. Print and search routines and the init routine, 10 points each, assuming you implement them the way we're describing in class. If you create a doubly linked list with code that you know has nothing to do with what we've talked about, you don't get your 10 points for those. So you got to follow the way that we're describing this. Add and delete are slightly harder because you need to remember the previous node to do what you're trying to do. So those are 14 points each. Your main program is 10 points. If you manage to free all of your memory and you have no errors from valgrind or warnings, and I'll tell you what valgrind is in a few minutes, you get 10% for that. If the compiler does not give you any warnings when it's run with the default settings, that's 5 points. If you get warnings, you'll lose 5 points. But if the compiler gives you warnings, you really, really want to take care of those. Because more than in 224, compiler warnings in this class are usually going to be fatal. But they're not going to be fatal at the point where the warning occurs. You'll get a warning about this line of code, but there's a good chance your program will continue beyond that line, and then somewhere later on, things will segfault. And the problem won't be, you know, in the statement right before the segfault. The problem will be this point previously in your program where you got a compiler warning. So make sure you deal with warnings. And then 3 points for each of the 4 coding style and comment requirements. Alright, so keeping in mind we haven't really talked about a lot of the C aspect of how to do this, but just from a higher level perspective, questions about this?
Won't lie, I'm intimidated.
It's an ambitious project, but it is absolutely within everybody's capability, and it will feel really good on the other side. And once you can do this, the rest of the course becomes relatively easy. This is sort of the first foray for most of us into data structures like this, and so there's some mechanics to get squared away, but there's also figuring out how to think about these things. But once we get on the other side of that, most of what we're going to do in this course will feel relatively straightforward. It may take a lot of effort, but the path will be fairly clear.
Good thing we went through this. I was getting a bit trigger happy, and I named my struct node instead of my node.
Okay.
I thought it was kind of weird.
Yeah. All right, cool. So let's look at some code. So let me see, what do I got here? So, general comment, when we're writing code in class here, I'm going to write lots of code. I'm kind of deliberately not going to necessarily write code that you can use verbatim in PA1. Right? I'm writing code to give you examples of how you can do things you'll need to do in PA1. But for example, I'm not going to call my structure a my node. I'm not going to call my next field a next node, and so on and so forth. I might use my data as a character instead of an integer next time. But the goal here is not the code itself, right? The code I write by itself is worthless. What you want to be trying to get out of this is sort of the higher level concepts of what is malloc, what is that star, what is that ampersand, what is that arrow, how do those relate to what we're trying to do here. So don't get too attached to the specific code. Think about larger concepts.
Will we lose points if we type def the struct?
That's totally fine as long as the struct is named correctly. You can use a type def so you don't have to say struct all the time. But if you use that type def inside your .h file, make sure the type def is also defined in the .h file, which I think would be the reasonable way to do it. Alright, so I'm going to make a sentinel node called sentinel. And my sentinel is going to be a pointer to a struct node. We're always going to deal with pointers in this class, right? Even though my sentinel is actually a struct node, I'm going to use the pointer to it. And I'm going to just write a statement in here which says, let's look at the thing the sentinel points to, that star sentinel. And that should be a struct node. And let's look at its data field and let's set that equal to 12. Or actually, let's just go ahead and do what we did in the assignment. So set let's set the sentinels.
Init function, like set the data equal to that number.
Yeah, you absolutely have to do that in the init function. So this is one of these things where if you tried to do this in main, you'd be violating that firewall. So yeah, that'll be part of init. But I'm not worried about abstract data types here. I'm just putting everything in my main program because we're just playing right now. So let's compile this, and I'm compiling it with a -G switch because I already know that when I run it, I'm going to get a seg fault. Alright, so let's GDB it, and let's start. And, you know, the first thing we're doing is we're saying take the thing sentinel points to, set its data field equal to this magic number, and that's sure enough where I'm getting the seg fault. Well, if I look at the value of sentinel, it's a 0. And so star sentinel is saying go to memory location 0, find a struct node at that address, and set the data field equal to this number. Well, memory location 0 does not exist. And it does not exist specifically so that if you do something like this, your program will get a seg fault. So sentinel needs to point somewhere. In our bogus memory maps, we were making sentinel pointed to 100 or 200, right? But we don't know what it should point to here, so we're going to use the malloc function. So we're going to malloc enough space for a struct node, and we're going to set sentinel equal to that. And you need to include standard lib.h to declare malloc. So let's put that in. So we'll compile and we'll run it in GDB and we'll start it. And we're going to say sentinel equals malloc. So before this happens, our sentinel is 0. Once we call the malloc function, if we print sentinel, it's got some funky value. And this is a location in the heap. And if we examine what's at that location, it's got a 0. But now if I execute the statement which says star sentinel.data equals magic value, and I re-examine that location, it's not 0 anymore. If I examine it as a decimal number, it's 1, 2, 3, 4, 5, 6, 7.
I noticed GCC likes to do that. It keeps stuff as hex 5555.
Mm-hmm.
Even on a Windows operating system, it does the same thing.
Interesting. How are you compiling on Windows? Are you using GCC?
I have a Windows subsystem for Linux.
Okay.
Using GCC.
Which is basically Ubuntu, I think.
Yeah, well, you can use multiple, but I'm specifically using Ubuntu. So.
Okay. So I think that's a function of GCC and the linker and possibly the operating system. But it's interesting that that works cross-platform. That's kind of cool. All right, so here's how we can create a sentinel node. And if we want to be really precise about this, I could set the next field equal to null. And uppercase NULL should be defined in our include files. So that creates a sentinel node. So let's start making a linked list by hand. I'm going to make a new node. I'm going to call it A, and I'm going to store a 10 in there. And I'm going to have my sentinel point to A, and I'm going to have A be the end of my linked list. And right now, I'm just going to write some C statements to create this list. And this is useful, you know, to get some practice with some of these constructs. And as you start to develop PA1, right, a print function is a really useful function to have. And if I can cobble together a linked list by writing a bunch of C statements, I can call my print function, and it should print out, you know, all the data values in my list. And once I have a print function that I believe, then writing things like insert and delete becomes easier because I have a way to look at my list by just calling print. So let's just cobble together a list by hand, and we'll do this in sort of the most straightforward way. So I'm going to make a node A, which is a pointer to a struct node. I'm going to set it equal to the return from malloc. And this is going to give me a different value from that. Every time I call malloc, I should get a new address in memory. And I'm going to set the data field of A to be 10. And I'll set the next field of A to be null. So I'm setting up that block right there. But now I want my sentinel to point to A. So I'm going to have to do something like this. Star sentinel.next equals A. Why can I do that? Because A is actually a memory address. It's the address in memory where this block is stored. And so this is going to be another thing that flip-flops between us as we move through this, thinking about A sometimes as a pointer and thinking about it sometimes as the actual node itself. And we may find ourselves sort of being sloppy in that reckoning of what A is, and that's actually okay. When I write a picture like this, I'm usually thinking of A as this actual block, even though in the back of my mind I know A is actually a pointer. But then when I say something like sentinel next equals A, right, to me it feels like, you know, I'm having this thing be, you know, it's not actually this thing getting shoved into this little lower half of the rectangle, right? It's the value that this points to being the location where this is stored.
So, I have one more question.
Mm-hmm.
So we talked about how our linked list here is going to be sorted by the value in data.
Mm-hmm.
And when I was making this a second ago, I kept trying to put the sentinel, which is has a value of 1, 2, 3, 4, 5, 6, 7 towards the end usually.
Mm-hmm.
That's a pretty big number.
Right.
Would you set something smaller to be the sentinel node?
No, just don't ever use the sentinel's data value. Always, when you start with the beginning of a list, you kind of skip over the sentinel.
Okay.
Right? So make sure that when you're looking for something bigger than the number you're trying to insert, or you're looking for something to delete, you start with the node the sentinel points to.
Okay.
Cool. Alright, so let's play with this in the debugger. So we're going to set the sentinel up to a node. We're going to set its data field. We're going to set its next field to null. We're going to make a new node called A. We're going to set its data equal to 10 and its next field equal to null. So if I print A, it's this big weird address in memory. If I examine what's at that address, that's the hex value for 10. And this is the next field, which is null. So now we're going to say sentinel's next field should be equal to A. So let's execute that. So what's the sentinel? Well, the sentinel is a location in memory where the sentinel is stored. If we look at that location, we find the sentinel's value. That's 1, 2, 3, 4, 5, 6, 7 written in hex. It's always followed by a blank 4 bytes. This is just padding. And then the next 8 bytes are the address where the next node is stored. So this block is the sentinel node. This first 12D687, that's this top half of the node. And these 2 byte sets down here, those taken together give me the bottom half of the block, the address of the next node, which should be the address of A. Well, I can examine this address in memory. And guess what? It's got an A. That's the number 10. And this location that I found, in the next field of the sentinel node, that's the value of A. And the variable A is the address where that node that I'm calling A is stored. So there's the number A, that's the data field. There's our filler. And these 2 8 bytes, these 2 4 byte sets are 0. That's the null telling me that 10 is the end of the list. Alright, so let's make this a little weirder. Let's make another node B. And let's put a 20 in there. And let's have A point to B. Now eventually we're going to do this inside code. But for now, I'm kind of doing it by hand. I'm writing C statements to do this, but I'm cobbling it together by hand. So I'm going to make a new node B. And I'm going to set B's data value to be 20. And B next will be null. And I'm going to set A's next field to be B. And I'm going to set the sentinel's next field to be A. So sentinel points to A points to B points to null. The sentinel has this bogus value, A has a 10, B has a 20. So what's the sentinel? It's this value down here. If I examine that location, there's the 1, 2, 3, 4, 5, 6, 7. This should be the address of the next node. And if I look at that location, there's the number 10 written in hex. and this should be the address of the next node. And if I look at that location, there's 14 hex, that's 20, that's the B node. And there's the next node, which is a 0, that's our null. So what's going on here? We're playing with GDB, right? GDB is good. We can go into GDB and we can start from our sentinel node and we can do what we want our code to do. We can look at the next field of the sentinel and follow that to A, and we can look at that node's next field and follow that to B. And we can see the data values in there and so on and so forth. Now, the code that we're working with here, you know, is relatively straightforward because it's just a bunch of assignment statements. And, you know, for development purposes, if I want to make a list that has two numbers, 10 and 20, I can do all of this. But in general, you know, when we're inserting things and deleting things and inserting more things and so on, we're not going to be able to look at our code and just see, you know, oh, B's next is null, A's next is B, and so on. This stuff is going to happen while the program's running. But in GDB, we can draw a picture of what our data structure looks like by following memory links. And so you're going to find yourself doing this kind of thing a fair amount. And if you have, you know, a nicely drawn picture to describe what your data structure should look like, you can use examine commands and print commands in GDB and see if that's what really is going on. You can also do things like print star sentinel.next. Look at the thing that sentinel is pointing to and look at its next field. Well, it's telling me right here, you know, the next field has a data value of 10, and that thing has a next field of this. So what's going on here? I'm saying sentinel is a pointer. Let's look at the thing it points to. That's the sentinel node. Let's look at that node's next field. Right? Well, that's a memory location. It should be the memory location of A. Let's look at that thing's data field. And there's a 10. But this is really, really cumbersome. So we don't want to write things like that. So I'm going to show you a shorthand now, and this is how you want to write statements that deal with pointers and dereferencing pointers. So sentinel is a pointer to a struct my node. So if I say star sentinel, that's a my node. And if I say dot next, this is a pointer to the first node of our list. And if I do this, this is actually the first node. It's the struct my node. And if I do this, this is the next field of the first node, which is the address of the second node. And if I do this, this is actually the second node, what we were calling B. And if I do this, this is the data in the second node. But this is a disaster, right? Unless you really like writing things like this, you probably don't want to write this. So there's a shorthand we can use in C, and this is the only way that you should be dereferencing pointers to structures from this point forward. So here's our shorthand. If we have a pointer to a structure, and we dereference it, and we pick off some field, we can do that same thing with the following notation: pointer arrow field. And this means exactly the same thing as that. But this is going to be a lot friendlier to use. So when you want to say dereference a pointer and access a field in that structure, just put the name of the pointer, put an arrow, and then the name of the field. So for example, if I have a sentinel, it's a pointer to a my struct. I can say go to the thing it points to and give me the next field. And this means the same thing as this. This will be whatever this next field contains. And since that is a pointer to a my node or a node, if I want to know the next field of that, I can simply say arrow next. And this says start at the sentinel, see what it points to, look at the next field, see what that points to, look at the next field of that. So this is a pointer to B, and if I said this arrow data, that should be B's value. And once you've made peace with this, when you write something like this or you read something like this, sentinel next data, you're going to think sentinel next data. And that's going to mean 20 to you. So let's see if that works. Let's print out the sentinel's next data. And that should be the value of B, which should be 20. So there we go. And GDB understands this also. So I can print sentinel arrow data. I can print sentinel arrow next. I can print sentinel arrow next arrow data, and that's a 10. Sentinel next is the address of our B node. Sentinel next data is the data of the B node. Sentinel next will be the next field of the B node, which is null, 0. And this is a whole lot nicer to work with than this. So we always want to use that shorthand. And again, the way to think about it is, you know, if you have some pointer and you want to dereference it and pick off some field, you can just say pointer, an arrow, which is a dash followed by a greater than sign, and then the field name. All right, questions about that?
So we can pretty much use that as like a way to set like a temporary variable to remember the previous set, right?
Yep.
Okay.
So we'll start writing some code on Tuesday to do things like, you know, we'll probably code up a print function that will actually do this following through from the sentinel node until it gets to the end. But it's you know, similar to what we're doing in GDB, but you know, for example, we could do something like this. We could have a temporary variable that's a pointer to a struct node, and we could say temp equals sentinel next. And then while temp is not null, print that node's data. So temp starts off being, you know, this first node that the sentinel points to, and if it's not null, print out its data. And then, here's the magic, temp equals temp arrow next. And that one statement right there makes everything work, because if this is temp, this statement says take the next field of this node, set temp equal to that. That basically changes temp to be this node. We go back to the top of our loop. Temp is not null, so we'll print out temp data. That's our 20. And if this, pointed to another node, we'll say temp equals temp arrow next. Well, temp arrow next is the address of this node. That's going to change temp to here. We'll come to the top of our loop. Temp's not null. We'll print temp arrow data. Well, that's the 30. At the end of our list, right, we'll say temp equals temp arrow next. Well, temp arrow next is null, so now temp's going to be equal to null. When we come up to the top of our loop, that will kick us out of our while loop. Because this says, well, temp is not null. Well, if temp is null, now we're going to come down here. And so we can print, a new line if we want, and we're done. And that's the mechanics for pretty much everything we're going to do. Insert, search, delete, and print.
And this is all going to be in a nested while loop, right? So we need an X to get out?
Yeah, you're going to put all of this inside. Well, so it depends, right? So the linked list code doesn't know about the X command or the I command or anything like that, right? But your main program is going to have a big long while loop that runs until the person says X. And it's going to call things like, insert and delete and print and so on. And those functions, insert, delete, print, and so on, will have loops like this in them.
Gotcha.
All right. So I will push this code over to the Linux server under the shared code area. And there's similar code from yesterday's class up there also. So suggestions for the next few days, right? You can definitely work on the main program. That's all CSE224 stuff. You can use this as a boilerplate to build a small linked list. And, you could add a few more nodes by making a node C, D, and E. And just cobble them together by hand. And then you could start trying to make your print function. And your print function is, basically this. And for starters, don't worry too much about naming conventions. Don't worry about structure and all that kind of stuff. Think about the code, right? And then start drawing pictures for things like insert and delete. All right, we'll talk about Valgrind on Tuesday, but there's some verbiage to it in yesterday's video from the other section if you want to know about Valgrind. Valgrind is a way to detect memory leaks. So basically when we're done, anything that we malloc, we're going to want to free. So we did a malloc up here, we did a malloc here, we did a malloc here. And if I just say valgrind main, at the end it will tell me I had memory leaks, right? I lost 16 bytes of memory. And it's because I allocated memory, but I didn't free all of it. And so we'll talk later about how to use the free function to clean up all the memory that we've allocated. All right. Have a good one. I will see you next time. Someone asked in chat, all PAs will have the same 4 file structures. Probably not. But I haven't written the other programming assignments yet, so I don't know. All right, that's all I got. Have a good one, and I will catch everybody next time.